Hello. Let's start talking about the existence and uniqueness theorem. It's been the last few minutes, or the next few minutes, talking about the theorem and maybe a reminder of some of its implications and just some important things. And then either depending on how timing goes, then we'll start talking about the proof of this theorem. So the existence and uniqueness theorem is shown here on this slide. I should point out that if you download this this PDF that I'm using as a background, there are actually two statements. The first one is just the existence part, and the second one, which is the one that we're looking at, is existence and uniqueness. And I'm going to focus on just the second one because, quite honestly, I've never seen a proof of just the existence theorem. I've only seen a proof of existence and uniqueness, this theorem that we have in front of us. So that's what we're going to talk about here for the next little bit. So we have some differential equation. It does not have to be autonomous. The right-hand side can depend both on t and x. So I have a differential equation and an initial condition. Both of those things are important because the existence and uniqueness theorem is about solutions to what are called initial value problems, which is a differential equation coupled with a given initial condition. And the hypotheses here, the most important ones, are that the function and the first derivative of f with respect to x are continuous functions on some open rectangle in the tx plane. So the picture that you should have here is that we have not very good axes. Here's the t-axis, here's the x-axis, and we have some rectangle. I wonder if I can make this dashed. I'll just make it thin. I have some rectangle, that's a pretty bad rectangle. We have some rectangle that goes from t equals a to t equals b, x equals c to x equals d. And it's an open rectangle, so those sides are not included in it. So this is that rectangle R that's referred to. And there's some initial condition that is in this rectangle. So there's some point in there that is t0 and x0. That's the coordinates of that point. And it says that we need the function f to be continuous and differentiable on that open rectangle. And then the conclusion is that there exists a unique solution, a unique function x of t that solves the given initial value problem. Now, there's one other thing that I need to highlight here, and it says that this function is defined for t0 minus epsilon is less than t0 plus epsilon. So the first important thing to note here is that this is what we call a local theorem. Only says that the solution exists near the starting point. So it's just going to give us, oops, let me bring that back so I can do this better. It's just going to give us a little piece of that curve. Who knows how much of that curve we're going to get, but it only gives us a little bit. There are other theorems out there that give you a clue as to that you can use to say how far you can extend that domain of definition of the function. But this theorem only gives you little chunks of it. And I'm going to outline the proof, and you're going to see in the proof where that comes from, why this only works for small t intervals around the initial condition. So that's the most important thing. And there's lots of theorems. We've already seen other functions in this class that are local theorems like that only give you a solution in a little bit. In particular, the implicit function and the inverse function theorem were local theorems in that way. So that's the most important part, is that it just gives you a little bit of a solution. But it would give you that solution for every point in this rectangle. It gives you a solution for every initial condition in that rectangle. The second thing to note is that I've stated this, that for X in R, but the proof, it works in higher dimensions. It's just when you do it in higher dimensions, this partial F partial X business being continuous, this now becomes a matrix. And other than that, it's all the same. I guess technically it becomes not a matrix. Yeah, no, it becomes a matrix. I was right. An n by n matrix. So I think that that's it for the notes. We already have a feeling for what this, some of the implications of this. So because we've used them a bunch, and so I'm not going to harp on this. So we know, for example, that something like this, the existence uniqueness theorem says that this can't happen. Right? You can't have a solution curve cross itself like that. And so and we've used that stuff a lot. I'm not going to harp on the applications, because we've sort of taken them all for granted. It also follows from the existence and uniqueness, essentially, the group properties flow from here as well for autonomous differential equations. All right, let's start talking about the proof. But before we even do that, before we prove it, I need to introduce a couple of tools for proving it. The first one here is the idea of is in definition 1, it's the idea of a metric space. And so a metric space is simply some topological space, and I should probably go and define that too, but we're not going to bother. So we get some space of things where there is a metric, a way of measuring distance. So a metric function is simply a distance function, and it gives us a way of measuring the distance between points. And there are mathematical objects out there that are not metric spaces. We, in a topology course, you would be introduced to these things, but here we're not going to worry about it. We have some way of measuring distance. We usually call that distance function, or at least I've called it here, a function d. And it really takes, it says it's a function from x to r, but really it's really a function from x cross x. So it takes two values in the metric space and returns a real number. The metrics does. And it has these three properties that are listed here. The first property is that the distance between any 2 points is greater than or equal to 0. That makes sense. It's a distance function. You can't have negative distances. With equality, if and only if x is equal to 0. X is equal to y. So the only way the distance between two objects in this metric space could be 0 is if it's the same point. The distance function should be commutative, that the distance between x and y is equal to the distance between y and x. Again, for distances, that's clear. For general functions, that might not be the case, but we would want that for a distance function. And the most important one, and generally the most difficult one to prove, that when you're trying to show that some function is a metric, is that it satisfies this last one: the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z. And you probably already know this. It's known as the triangle inequality. And that's usually the one that takes some finesse to prove. So some examples uh, absolute value on the real line is a distance function. And another example would be the distance between x and y is equal to the square root of x1 minus y1 squared plus x2 minus y2 squared. And then the square root of all that. On R2. That's just these are called the Euclidean metrics. These are not the only metrics on R2 or R3, right? And we could generalize this to R3 and Rn in general, this distance. There are other distances, and sometimes there are good reasons to use them. We really don't need to do that. Let's see. What did I want to say next? I know. Usually, we don't use the letter D. It's handy for the definition, but usually we don't use it. Usually we would say we'd either use this, absolute value signs, even though we may or may not mean the usual sense of absolute value, or sometimes we use like double absolute value signs. We sometimes use the word norm to describe this. But this is the common notation. And this is the notation that we are going to use going forward. Finally, my last note is this, is that our metric space is a space of C1, so that's continuous with a continuous derivative functions on R. So our metric space consists of functions. And so in other words, points are functions. So elements in this space might be e to the t, or t squared, or t cubed. Absolute value of t around 0 is not going to be an element of the space because it's not differentiable. The square root of t minus 3 is not a function, or x minus 3, whatever the letter is not going to be a function, not a point in the space. So that's why we need to introduce the idea of metric spaces, because the distance that we're going to be computing is the distance between functions. And again, there are ways to do this that I'm going to kind of not worry too much about here in this proof. Again, this is in the real analysis course, in what is that, 331. This is certainly a topic that should be covered in 331, is distances in function spaces. And how we use those. But that is not, we're just going to use it. I'm going to just sketch this proof, so I'm going to use the idea. All right, so that's the first piece of background. The second piece of background is theorem 3 down here that we're going to use. It's called the contraction mapping theorem. And the contraction mapping theorem says, well, I have to tell you what a contraction mapping is, but that's inherent in the theorem. It gives us a way of finding a unique fixed point for some function on that metric space X. It says, let X be a metric space. Okay, so technically it needs to be a complete metric space. Those of you who are in 357 with Jeff and used my book in the fall, there was some time spent to this theorem and the idea of complete metric spaces. But it says, let X be a metric space and F a function from X to X. And it says, suppose that there exists some mu that is greater than 0 but less than 1, and the distance between f of x and f of y is less than mu, and there's a typo, that should be the letter mu, not the word mu. So it says, so I have x and y, I apply f to it, their distance, actually this whole thing is wrong. This should be, so let's just get rid of this. Let's fix this to the distance between f of x and f of y is less than or equal to mu times the distance between x and y. So that is the correct statement for that hypothesis. It says, then there exists a unique x star in x such that f of x star is equal to x star. That x star is called a fixed point. And so basically what the contraction mapping says, so let's think about the hypothesis. The distance between f of x and f of y is less than mu times the distance between x and y. Remember, mu is less than 1. So I start off with any 2 points in that space. They're some distance apart. I then apply f to those points. And the resulting thing is not that the resulting 2 points, wherever they happen to be, are now closer together than they were at first. And the rate at which they got closer is mu. So mu is the contraction factor, how much closer they got. And it says, and again, if you think about this, this is somewhat obvious, just sort of intuitive, that if I take any 2 points and every time I apply f to them, the points get closer and closer and closer, then it seems like they should all be going to some one place. That you can't have points getting closer, but these points in my left hand going off to here, and these points in my right hand going off to here, because those points just got farther away, right? So somehow things have to march together to the same conclusion. They have to go to the same fixed point. All right, so those are our 2 main tools, is to look at a metric space that consists of functions and the contraction mapping theorem. And we will apply this theorem to our function space. And our function space will be the space of possible solutions to the differential equation. All right, I'm going to stop here. In the next video, I'm going to illustrate how we're going to do that. I'm going to illustrate the function that we are going to be iterating on a function space, and I'm going to do an example of that iteration, and you will see in the example that I do it converging to the thing that we know is the solution to the differential equation. All right, so that's the next is to build just a little bit more on that.